presented by Dr. Chen and myself. The topic for today's presentation is ARSpy. So the augmented reality brings digital information and virtual objects into the physical space. With the AR, the digital world come to life inside the view captured by your tablet or phone camera. Basically, there are three types of AR: the marker-based AR, markerless, and location-based AR. In the marker-based AR, the digital world is anchored to the real world. For example, let's say I want to display an educational animation right on to the page of a book. The first thing we need to do is we need to know that the user is pointing the camera at the right page, right? And this can be achieved by placing a distinctive picture on the page. We call this distinctive picture that can be recognized by the device, the marker. A marker can be anything as long as it has enough unique visual points. On the contrary, the markerless AR means the application does not need an anchor to the real world. So basically, the object just flows in the middle of the air. The third type of AR is the location-based AR, which is the focus of this paper. Location-based AR ties the virtual world to a specific location. Typically, they use GPS and simultaneous localization and mapping techniques to determine a user's location and to detect a device orientation. The successful applications that create a more immersive experience, including the games like the Pokemon Go and AR-based airport pathfinding at Gatwick Airport in London. Due to the great potential of the location-based AR, many third parties provide a full-featured software development kit, the SDK, that allows developers to build location-based AR application without concern for technical details like the motion tracking, proximity calculation, or scale estimation. Here is the summary of the software development kit that are very popular right now. As you can see here, most of them provide location-based and cloud-based services to enable location-based multiplayer AR experience. Moreover, most of them also issue a free license for the users to use. Before we actually dive into the attack and the mitigation strategies, let us first look at how does a location-based AR application work with the third-party SDK. In detail, the sensor data such as the video frames and the geolocation data gonna be sent to the SDK-enabled logic layer of location-based AR applications. And the location-based AR application process the raw sensor data and request the corresponding AR contents from the cloud-based data set that is maintained by content providers. Then the request the AR contents are downloaded to location-based AR application. You may wonder why we're going to use a cloud-based database, right? So we have many reasons for that. For example, the business and the scale of economics, the security, so on and so forth. For location-based AR system, the network traffic is much larger than the conventional location-based services, such as the weather report and navigation. Due to the large size of AR contents, the AR application only cache those AR content that are within a certain distance from the AR user, which enables the attacker to estimate the location of the AR user by detecting a distinctive pattern in the network traffic. Moreover, to support the location-based multiplayer AR experience, users can upload or delete their AR contents with real-world GPS coordinates to the cloud database and also download AR contents when they reach those real-world GPS coordinates. The location-based AR application also continuously analyzes the GPS location of the device in order to download AR contents at the GPS location and to anchor AR objects on the screen. Therefore, without mitigation solution in the SDK level, the location-based and cloud-based services can be used to infer the real-time location information. Here is the key insight. So basically in this paper, we explore the security threat model of AR devices and demonstrate a new side channel threat that caused by location-based AR applications unique combination of a very high volume of real-time data and outsourced geolocation processing. In short, if the downloading or uploading job are location related, the location information may be leaked. Okay, so now let me hand the presentation to my colleague, Dr. Chen.
Okay, so can everybody see the screen, right? Okay. So here in this study, we consider a capability restrict attacker that aiming at revealing the location of users of some AR applications. So as you can see, here is our adversary model. We consider that the adversary only has the access right, no more than that of a standard user. So basically that means the adversary or the attacker cannot like directly hack to the server to retrieve all this location information. Instead, they can only like just get access to the server, like just like a normal user. The only exception is that it can manipulate, aka spoof, its location. This is a quite like well-known like issues because even for like this like Pokemon Go or some like existing like location-based AR applications, spoofing this its own geolocation is just is still available for some. It's still possible. So therefore, that's the first rule of the adverse model we consider. And the second one is that we said that the attacker can trick the victims into installing malicious applications that only require non-system permissions. So that being said, it means that when they install these malicious apps, this app only says that I'm going to probably check some of your phone status. I'm not going to like get your GPS locations. Okay, so now that's basically the adversary model that we defined here. All right, so here, let's take a look at this overview of the attack. So in the real attack, the attack settings, there's actually three entities in this figure. We have the victim here, right? So the victim is using the AR devices. In our experiment, we're just using the smartphones, but in future, that could be like AR glasses or some other devices. And we have the attacker here, where the attacker is trying to like craft some like fake AR content. And the third one is the AR cloud database, right? So we have three entities. So as you can see, the victims using the AR devices to interact with the AR cloud database. So the victim's AR devices will send its current location of the victims, and then the AR database will download all the AR content, for example, the content of like a 3D model, or maybe some like text or some other information advertisement for this surrounding area. So it could be any content. Okay. So here is the overview of the attack. So a complete attack can be divided into 5 steps. The first step is that the attacker uploads several specially crafted geo objects. It's like some advertisement, some AR model with a fake location to the cloud database. So if you see this figure, you can see that those like crafted this AR contents being like be colored as this light red color. So that's going to be the malicious content, and they will be sending directly to the cloud database. And then the victim on the other side, in step 2, the victim will post his or her current location to core the database. This actually happens automatically, just like when you play, like when we use an app like Pokemon Go or like Instagram, not Instagram, but some other like geolocation-related apps, they'll actually happens automatically. Then on the third steps, the database will start to return several geo objects back to the victims, including the craft objects. So you can see that the green one is actually the one that's supposed to be here, and then the red one is the attacker's the malicious content. So both of them will be downloaded to the victim's devices. And the victim, once they download these objects, then it will create a unique traffic pattern. So the attacker basically try to utilize the malicious application to keep monitoring the victim's traffic pattern and use the reported pattern to reveal the location of the user. So that's the overview of the attack. So you can see that in this attack, once the attacker upload all this malicious content to the cloud database, then the attacker can simply just sitting there and then simply just keep monitoring the network bandwidth or the throughput of the victim. All right, so we start to see whether, or to try to run some experiment to see whether if it's this key insight works or not. So we first do some feasibility study. So we know that in order to run this type of attack, the attacker needs to first trick the victims into installing its malicious applications. And this application only supposed to require non-location related permissions to monitor network throughput of the target AR application. So the permission needed for those for this malicious application is simply just say read phone status and identity, which is the word that we pick for this Android platforms. You can see that from this chart, the popular mobile applications that ask for read phone status and identity permission it's very common. Most of all these applications that we found here has a large number of installations. So when the user install those non-malicious apps or this potentially malicious apps, the user will think that they probably just read the phone status. They will not leak your location information. They're not going to read the GPS information. And then the attacker also, the third step, the attacker also need to manipulate and its geolocation and deploy the fake AR content. So we first studied several state-of-the-art AR applications and SDKs and find that these AR application SDKs basically try to send those local information or this geo information to the server using a simple HTTPS GET request. And on the server side, after getting the request from the client, the AR server serialized return information into structured data using the HTTP protocol and return it into sending back to the AR application. So this basically just means that we're sending the geo information and then we download the AR content. And we also run some extended studies and we just figure out that all the existing AR application and AR SDK is basically all based on the same mechanisms. Okay. So therefore we asked volunteers, we hired some volunteers and to use our self-made AR applications and working among 3 locations on campus. So you can see that this is our initial experiment and the result. So first we play some AR content on 3 locations, and then we ask the volunteers to use their AR devices, their smartphones, and walking through it, and we'll open this AR application. And you can see that after the users approach to the first location, then the downloads will be start to triggered, and then here is the network throughput. Right. This is the first. We actually run this initial experiment twice, and then see that each time they have a similar download pattern. And then once they reach to the second location, then here's the network throughput pattern look like this. And then finally the third location. So you can see that every time the user approach to a certain location, the AR application starts downloading, which will generate a certain pattern. Right? So, and then we find that it's probably going to work. So therefore, we try to propose this coarse grained location detection. So we try to locate the victim in a detected region. So the basic idea is try to cut the region into several non-overlapped areas, just like the one shows in this figure. So each area is a circle whose center is the location of the AR contents, and the radius is the searching range of the AR application. So therefore, we'll make sure that each time the user step into that region, then this AR application will start to downloading AR content. And the size of the AR content in one area is distinct from the other in any other area. So therefore, we can distinguish that one from the other location. We can uniquely pinpoint that location. And we know that this coarse-grained location detection algorithm has two key limitations. First, it cannot cover all locations in the small region, since the searching area of each AR content is a circle. Second, the localization granularity is relatively coarse. So in that case, we can only achieve, we can probably just like find the roughly the where this users is like the victim is located, but we cannot like precisely pinpoint its location. And therefore, we propose another a better location detection mechanism is called the fine-grained. This one we try to deploy the AR content by using a method, a combined method. One is called the space partition, and the second one is the strip-based space coverage strategy. So we first try to divide the target area into 4 non-overlapping regions, and we try to pinpoint the victim in the space to precisely one of the regions. So you can see that by placing the AR content in a very dense way, and then by using this strip-based space coverage strategy to make sure that each AR content is uniquely covered to a certain piece of space. Therefore, we can greatly improve the location, localization accuracy. So so for the fine-grained location detection, the most important thing is how to generate this AR content, or to be more specific, what is the size of the AR content for each region? Because we want to make sure that we can cover all this space, and also we want to make sure that any combination of the AR content is still a unique number. Because if there's multiple ways, if you simply just generate this AR content with a random size, then the combination of the of multiple adjacent grade, it could be it result into the same size, and therefore you have it's impossible to detect the real locations. So therefore we choose the idea of using mathematical equations called the super increasing sequence, where we use this where we make sure that each content size, for example WK, it should be greater than all the other content size, the summation of all the rest of the content. So therefore, by using this super increasing sequence, it's guaranteed that for each unique overlap space, it has its unique size of the AR content. And also we find that a better way to attack in this fine-grained location is to apply this so-called recursive region detection, where we try, because if we simply just placing all this super increasing sequence, then the size rises rapidly. So therefore we find, or we just make it impossible to cover a very large area. So in that case, we try to use the idea of this divide and conquer. So for a large space, we first just use this super increasing sequence to deploy the content, but with the same size. And once we detect the user is within certain range, then we just re-upload this AR content with a different with a different size, and therefore to and shrink the detection area. And eventually we can make it smaller and then successfully pinpoint this the user's location. So the fine-grained location detection, after we successfully detect this AR content, the next thing is how to process the network traffic information. So we know that in the real world scenario, once you run this experiment, the network traffic contains a lot of noise. So we need to first run through this noise removal and also accumulate the sum of the throughput numbers together. And we try to eliminate some small traffic that cannot be maybe just caused due to this not caused due to the AR content, but some maybe some errors or some other issues, some interference issues. And we try to accumulate the network throughput within the moving time window. So in that case, we can you can see from here, we can use this by using this our traffic processing algorithms. We should be able to successfully calculate the actual network throughput for each position, for each location. And here in order to run this experiment and test our ideas and systems, we build a real world test bed in order to effectively evaluate the attack method we propose. So we first we built like 2 Android applications. The first Android application is just for monitoring the network traffic. It's just try to mimic the one that the attacker tricked the user to install. And also we built the Android application for intimating the behaviors of the AR applications. So this is actually a benign one. This one will not like steal the user's information. And then we also have a customized location provider for the location spoofing and backend AR server. We also built a simple graphic user interface to help the subject to collect data. Okay. So while we're building this one, there's several technical issues we need to conquer. So first one is how to monitor the network traffic. So the core part of our system is try to accurately monitoring the network traffic of a specific application. To achieve this goal, we study the feasibility of monitoring network traffic on the Android platforms. So we find that for the Android platforms, you can use this network status manager to this service provide access to network usage history and statistics of other applications, which enables an attacker to implement a listener in another application on victim's device. And we also create this this malicious software as a background service, which allows us to can log the total network usage in every second, and the throughput of each second was acquired by calculate the difference between the neighboring entities in the log files, and eventually generate the result. So for location spoofing, there's multiple ways to do this. Well, because we just try to do this as a proof of concept experiment. So we choose to use the there's in the Android system there, once you enable the develop options, you can enable this allow mock locations on these Android devices. And therefore, once we allow this, once we enable this option, then the attacker can simply just feed in any GPS locations and then talk to directly use that fake location to upload content, AR content to the cloud AR database. So here is the performance evaluation. So to evaluate the performance of our tag model, we first conduct the experiment on our testbed on campus. So for the coarse-grained location detection, we ask the volunteer to walk through a path. And on the path, we first uniformly pick 8 locations, and then the distance between the neighboring locations was about 6 meters. So that basically restricts that, being said that the accuracy for each one is about 6 meters if we can successfully pinpoint that location of the user. And the searching range of each location was set different values to evaluate the performance of our tag strategies. Okay. And then for a fine-grained location detection, we set a searching radius is about 45 meters. We developed the AR content whose total size follow the rule of super increasing sequence at each location. And the minimum size of the deployed AR content was also 1 kilobyte. So here shows you the performance evaluation result. So you can see that for the coarse-grained detection and fine-grained detection for a single location, you can see that from this figure we have 8 locations, and our coarse-grained location detection strategy can locate the victims in non-overlap areas with a mean accuracy of about 94.6%. And for the fine-grained strategy, can provide a better average accuracy of about 97.1%. So that's the overall performance evaluation of our system. Of course, there's a trade-off in how densely an attacker should deploy the AR content in a small region. we find that if we deploy AR content at many different locations, we can certainly just estimate the victim's location with a better granularity. But the problem is the location detection accuracy may not be good due to the inaccurate GPS coordinate. That is sometimes due to the interference of the buildings or the environment. So we find that the fewer locations where we deploy the AR contents, usually we get better detection accuracy. But more details of the victim's trajectories are lost. So here we actually, this is the figure, the result that we test with the three different settings of the searching distance. So of the distance between the neighboring locations. So you can see that with the distance equal to 70 meters, we can achieve around nearly 100% accuracy. And then once you lower the distance between the neighboring locations, for example, once you reach, set it as a 13 meter, then the accuracy actually dropped to 60%. So you're probably gonna wonder why there's no some figures more details. I mean, more points, data points. This is because this experiments actually very time consuming. We need to hire a lot of volunteers working on the same path over and over again. So, and there's also some other ongoing experiment at the same time. So therefore we choose the 3 meters, and then which can somehow shows us the result, the idea. And also we evaluate our systems, try to figure out the performance on different paths to see whether if say the users working on different paths could potentially impact our attacking algorithms. So you can see that the users, the volunteers are required to ask to work in 3 different locations, 3 paths. One is the color in this red rectangle, and the other is this black dot, and then this yellow triangle. So we find that the average location difference, the result is shown in this figure. You can see that there actually has some performance difference for different paths. The performance may vary because due to the interference or some other thing of the GPS signal. But overall, the location detection accuracy is beyond 85%, which is still considered good. And we also try to run our experiment on different type of devices. We run this one, we ask the volunteer to first carry out the Nexus 6 Android phone. Then we also use Nexus 5, and then with the same, ask them to do the same, exactly same experiment with the same path. And we find that the Nexus 6 has a better performance than the Nexus 5. This is due to the following reasons. First is the sampling rate of the GPS data. Nexus 6 allows the app to sampling the GPS data with every 1 second. But Nexus 5 usually, even if you set for 1 second, this usually allows the sampling rate is actually more than 1 second. The second one is the maximal delay of receiving the next GPS coordinate for each system, each smartphones. Due to the hardware restrictions, they actually said that Nexus 6 allows the user to wait for 12 seconds to receive the next GPS coordinate. So you can consider it's just like the cooldown time. Well, the Nexus 5, the cooldown time is around 22 seconds. So that's the previous experiments is all about this short-term, just maybe one round attack. So therefore, the goal of those kind of experiments is try to see whether our attack, this algorithm can successfully reconstruct the working trajectories of the user or the victims. And then we also try to perform some long-term attack to see whether our system, the proposed idea can review the top N locations of the victims. So what is the top N locations? For example, you see that when we talk about top 1 location, this that location probably is your home, right? So that's where you live. And then top 2 probably is home and work for most of the people, right? So when there's a paper that published 7 years ago said that in Science magazine, I guess, they said that by simply just using the top 3 locations, you can easily infer the to review the identity of the user. So that being said, the top N location is very useful because we can use that to infer from the human mobility data and to reveal the identity of the user. So we just run this experiment, long-term experiment, and we find out our attack method is able to deduce at least top 4 locations for more than 50% of the accuracy of the user. For more than 50% of the user. And we can achieve 86% detection rate for the top 2 and above locations, the home and the workplace. So therefore, you can see that this proposed this AR security threat is also able to review the user's top 4 locations. So so this is the just this type of new attacks basically allows the attacker to simply just use this side channel information to by simply just monitoring the side channel band network throughput information, can use that to review the real location of the user. So we kind of think, is there a way to to prevent such things, right? So here is the mitigation mechanisms that we proposed. The first one is that we say that the SDK providers or developers can deploy and maintain an active cache with a variable size to store the AR content on their client side. So therefore, once the users walking, the app should say not immediately downloading all the content, AR content information. They can do some preloading or some pre-caching things. So therefore, this AR content is not tied to this the user's location. The second mitigation method that we think it probably going to work is to add some limitations. Like any user, AR users cannot deploy too many AR content at a single location. Meanwhile, the size of each AR content should not be too large. But this one looks okay, but the problem is sometimes, let's say that when you build this large AR systems, then the attacker can still bypass this kind of defense strategy by creating a lot of fake account, and then for each account they only submit some certain AR content, a very small one, but eventually they can, once you aggregate all of them together, they still might be able to bypass this kind of restrictions. But still, adding this limitation will certainly make this attack more harder than this without it. So the third one is the another method is to further limit the permission of the network traffic monitoring on the victim's device. Because at current stage, we all thought that the network traffic is okay to monitoring because it does not contain any sensitive information. But in this research, we just showed that this network traffic could potentially leak the user's locations, which means the third-party application cannot get the network traffic information. That will make this attack even harder, right? So for the future directions, because these AR devices probably will become popular in the future. So the current research, most of the research is actually focused on whether it is possible to create a robust AR application to avoid those AR content covered by this malicious object. For example, the one that shows here, this is a car's dashboard, and then they use some AR techniques to display those AR content. So most of our kind of research is focused on how to prevent displaying too many AR content to cover the whole dashboard, and then that will be very dangerous for the driver, right? But we just showed that from this research, we also showed that this visual AR applications, because once you turn on those sensors, like the camera and the GPS sensor and all the accelerometer and gyroscope, all these sensors, then they will start to capturing all the information from this surrounding area, from the environment around this user. So they could raise serious privacy concerns, and it could incur new challenges, right? So we need to figure out to carefully to think each and every like mechanism and see whether there's a eventually create some like new side channels and then potentially leak some users' information. Right. So I think that's all for today for my presentation. So any questions?
All right. Thank you so much. That was great. So let's give first of all, again, thank you for your great presentation. Let's give the participants a couple minutes. If you have questions, feel free to type your questions into the chat, and we will start with that.
Also, feel free to unmute your microphone too, if you'd rather just go ahead and start asking. All right, well, I'm going to say that there are, there we go. No question here. Very appreciative. Thank you.
Thank you.
All right, well, if nobody has any questions, feel free if you see or Liu, if you want to drop your contact information in the chat,
Sure.
if anybody would want to get a hold of you after the presentation. But if there are no questions, we will go ahead and end this session for today. Thank you so much for your time. Thank you for coming today, and thank you for taking the time to present to us. And this recording and slides will be available on the CA community website within 48 hours of the presentation, and you can find it there. Thank you, everyone. Oh,
Thank you.
we have a question. Lauren, do you want to? I'll go ahead and stop recording.
Hi, guys. I beg your pardon for using this.